State Center, Computer Society of India Trivandrum Chapter, PMI Kerala Chapter, Internet Society Trivandrum Chapter, Vakkom Moulavi Trust Trivandrum, and IEEE EMBS Kerala Chapter. Before we start, I wish you all a happy new year. Let this new beginning bring you a prosperous and blissful new year. As you all know, we are gathered here to listen to the knowledgeable words of our eminent speaker of the day, Dr. Elias Towe, who is a professor in Computer Science Department, Carnegie Mellon University, Pittsburgh. It is an occasion like this where we get opportunities to test our knowledge and understanding. We look forward to get an exposure about what the best of the brains think about this very dynamic topic. The promise and implication of quantum science and technology, a revolution like no other. It is time we begin the event. Now I call upon Adina Nixon from IEEE for the welcome speech. Ma'am, please.
Thank you, Ms. Bhagyashree. If your actions inspire others to dream more, learn more, do more, and become more, you are a leader. A very good evening to everyone present here. With warm greeting, let me welcome you all to the 39th program of Intersociety webinar series. Today, we aim to discuss on the topic, the promise and implication of quantum science and technology, a revolution like no other. To talk about the topic, with immense pleasure, let me welcome Professor Elias Towe, PhD in Computer Science Department at Carnegie Mellon University, Pittsburgh. He was educated at MIT, where he received the SB, SM, and PhD degrees from Department of Electrical Engineering and Computer Science. Dr. Towe is a recipient of several awards and honors. He is currently a professor of Electrical and Computer Engineering and also Material Science and Engineering. It's a great honor for me to welcome you, sir, to share your knowledge and thoughts for today's session. Welcome, sir. I also welcome all of the distinguished personalities gathered here for the session. Once again, I cordially welcome you all to this event. Thank you.
Thank you, ma'am. Now let me welcome Dr. Sajida Bashir to introduce our speaker. Ma'am, please.
Yes, thank you and Happy New Year to everyone. It's my great pleasure to introduce a friend and I would say in some ways a colleague, Professor Elias Towe, as the first speaker of the 2021 Intersociety weekly meetings, which are jointly organized by a number of professional and social organizations in Kerala. The topic, as you know, is quantum science and technology. And for those of us who are not physicists or engineers, this topic is quite abstruse. We know about the quantum revolution launched by Albert Einstein, vaguely know that all the advances that we see in computer science and information technology is related to the discovery that particles also act like waves. And the engineers amongst us, of course, know a lot more. But I think the understanding of this ongoing second quantum revolution, which includes the application of quantum principles to create new materials to computing and information science and to communications, this is perhaps not so widely understood even in the scientific and engineering communities, much less so amongst policymakers. Professor Towe is an outstanding expert in this field, and I believe he's one of the best speakers we could have had for this topic. He has a difficult task balancing act to do to speak to both engineers and other professionals. As already mentioned, he's a professor at Carnegie Mellon University in Pittsburgh, United States, where he teaches in both the departments of electrical and computer engineering, as well as material science and engineering. His broad research interests are in quantum photonics for information processing and sensing. He's an IEEE Fellow and a holder of many awards. Over his distinguished academic career, he has published over 170 peer-reviewed technical papers in professional journals, and he's received all his degrees from MIT. But these academic distinctions are not the only reason that we invited him to deliver this talk. He is deeply concerned about building technical and scientific capacity in developing countries, including Africa. He originally comes from Uganda, and in this sense, he exemplifies the mission of IEEE to advance technology for the benefit of humanity. So before I hand over to him, I would just say there's only one thing I would have claimed to have taught, in quotes, Professor Towe. During one of our conversations, he asked me if I knew of an organization called IEEE and started explaining what it was. After listening to him for 1 minute, I took the liberty of interrupting him and saying that I came from Kerala, and if a person doesn't know what is IEEE, then they really could not belong to Kerala society. So I'm very grateful to him for accepting this invitation and look forward to his talk. Professor Towe, the floor is yours.
Thank you, Sajida. Thank you, everyone, and good evening and Happy New Year. I'm honored to be able to tell you a little bit about this fascinating area that I've been involved in for a while. I'm going to turn up my video to conserve bandwidth. Okay, so the quantum revolution. We've actually been living through one. Most people probably haven't been aware of it. If you're not an engineer, you probably are not aware that that's what we've been living through. And it turns out we are going through one. The simplest example is in the semiconductors that run your mobile phones, your computers, your televisions, and any other electronic gadget that you might have. Before that, one of the most important things that this revolution enabled was precision timing and metrology. Those are very obtruse to the non-technical person, but in order to be able to make any semiconductors that are going to be fashioned into devices that would run your electronics, you need metrology. Metrology is the art of measurement and the art of creating things that actually conform to certain metrics or measuring yardsticks. And so that was one of the things that was established initially. And then timing is also important. If you have a GPS, which most people do on their phones, you need satellite timing to be able to precisely locate you on a particular location on Earth. The signal has to go from the ground to the satellite and back again. And the measurement of the time determines how far you are from whatever it is you're trying to go to, because of the fact that we know that the speed of light or speed of electromagnetic energy is a given constant. And knowing that speed, knowing the time, you can determine the distances. So that's why these two components are very, very important. What the revolution that we've been living through mostly has offered us is an ability to understand nature as it is, okay? And what I say nature as it is we have been able to really figure out how semiconductors work and materials in general, how they work from the atomic level up. And with that knowledge, we're able to perfect them. And when I say perfection, I'm talking about placement of atoms precisely where they are. We don't do that at the moment, but what we've been able to do is to create conditions that allow the semiconductors or the materials to be at their most perfect so that they can display certain macroscopic properties that you can basically use classical laws of physics, Newton's physics, to be able to understand how the devices behave. And that's really what we've been living through, the understanding of the materials at the lowest level, and then allowing nature to perfect the formation of these materials without too much interference from us, so that we can use the laws to basically do what we want. In this particular case is to allow electrons to be able to travel and route it in the semiconductors to precise the location that we want them to be at, and to switch on and off when we want them to. And that's how we've been able to make the semiconductors that we have. What we've been doing all along is reducing the size of the basic element, which is the transistor. And when you reduce that basic element, you increase the speed. We are now at the latest technology released in September, in the latest generation of iPhones by Apple, are sporting 7 nanometer dimensions. That's the minimum dimensions of one of the devices, which basically means that they can pack billions and billions of these devices into a single chip. So they can allow you to run the fancy applications that you can now run on your phone instead of a normal computer. The next revolution is essentially moving away from that. And the reason we're going to move away from that is because we now recognize that as we get smaller and smaller in the size of the devices, we are actually reaching the point where the number of atoms is now becoming countable. And when they become countable, that basically means the laws of quantum mechanics now take over. And we might as well begin to now create materials or structures where the laws of quantum mechanics are operative. Up to that point, we've been using Newton's laws. So that's really the reason why this second revolution is going to happen. We're now finally going to take advantage of the quantum properties at their level. So here's the rest of the agenda for what I'd like to tell you. Given the diversity of the audience, I thought I would give a brief history of quantum theory and an example of what it's enabled us to do. And I'm going to use an example from my laboratory. There are a lot of other examples out there, but I figured it would be easier to demonstrate what I'm talking about using something that my group has done. And then discuss what the promise really is going forward in this technology. And then look at how the world is reacting and investing in this field. And finally, discuss the implications of the technology for both the societies that are able to afford to invest in it and for those that cannot. So how did quantum technology begin? Well, it began in 1896, actually. So it's over 120 years old. There was this phenomena, if you've ever been in front of a firewood, a fire that's basically started with wood, what you realize is that the embers of the fire, when you initially started, they start off like orange colorish, and then eventually they turn whitish. That distribution of heat can be measured. And that really was the problem that scientists were beginning, or at least attempting to understand. And they were able to measure the distribution of the heat as a function of frequency, or as a function of the wavelength of the light that was coming out. And the graphic on the left-hand side basically illustrates what that distribution is like. So you get the visible colors, and those are essentially the colors that you initially see when you set up a fire, okay, in the visible color. But there are other colors that you really cannot see because your eyes are not equipped, or your eyes are not made to see those colors, okay? And they were able to measure that. And then the next question that was asked was, is there a physical law that we could use for understanding how that distribution behaves the way it does? Several were tried, and one of the ones that failed, and it became called the ultraviolet catastrophe, was by Rayleigh and Jeans in the UK. And it woefully failed to describe the distribution at the lower wavelengths. And then comes along a German scientist called Viton. He basically suggested an ad hoc formula, meaning there was no basis for it. It was just something that he felt would fit experiments. And he described the density of the energy as proportional to the frequency cubed, and then exponentially decreasing with temperature and frequency at the same time. When he tried to do this, it was a better fit than the Rayleigh law. However, it also failed at the lower frequencies, meaning that this time it failed at the higher wavelengths, okay? And this was a disaster for the scientists of the time. And another scientist by the name of Planck, by this time it was about 1900, decided that there must be a different way of trying to understand the light that's being emitted in the form of heat, okay? And he thought maybe instead of assuming that it was distributed continuously, okay, maybe it was emitted in bundles of light. And by making that assumption, he fitted a new formula, and that formula perfectly fit the distribution of heat from what was then called a black body. That's essentially what we call a fire when it's confined to a space. We call it a black body because it emits and absorbs all colors of the spectrum. And So he decided that there was a constant of proportionality. The energy was proportional to frequency, and there was this constant. It was a very tiny number, okay? And he called it basically a constant. Later on, people started calling it Planck's constant, and it turns out to be a very, very major characteristic constant. That's the basis of all of quantum mechanics today. The second manifestation of the strange behavior of nature was when Hertz, for those of you who are electrical engineers, you recognize the name Hertz from his experiments with antennas and metals. He measured this strange phenomenon where electrons were being kicked off a metal when you shine light to it. And he was able to basically design this crude experiment where you have two metal electrodes, you apply a bias and ground it, and you're able to measure current flowing through the device. And then what he noticed was that no matter what color of light you used, no matter what intensity of light you used, it didn't change the current. On the other hand, if you change the color of light, which is equivalent to changing the frequency, something different would happen. And he failed to explain that. And then of course comes along Einstein. And Einstein basically said, all right, let's try Planck's assumption of quanta. Maybe electrons are kicked off by bundles of the light energy. And again, using that assumption, he was able to fit the data extremely well, confirming Planck's hypothesis. So armed with this knowledge, the Danish scientist Bohr decided that it was time to find a model for understanding how the atom actually works. And earlier on, Rutherford at Cambridge had basically tried to measure where the atom is and what's around it. And he had found that it was void, meaning that it was surrounded by mostly empty space except for the center part of it. And Bohr tried to understand that. And he said, all right, if we assume that there's a nucleus at the center and there are electrons orbiting that nucleus, and each orbit is of a specific energy and size. When you use that argument, it seems to work. Okay, the problem was, it was running into problems with one of Newton's laws, which basically required the electron to eventually smash into the neutron, but no one noticed that happening. So there must have been a problem with the law that Bohr had suggested with the model. So it didn't really predict or agree with most experiments. So a lot of people came to help with trying to establish a law that would actually correctly predict these experiments. Several of these people are listed in this chart. One of them was Pauli. Pauli basically said maybe there are actually some rules of how these orbits that Bohr is talking about should be occupied. And then Heisenberg comes along and says, well, maybe there's also an uncertainty in how precisely we can measure some of these variables. And he came up with the uncertainty principle. And then finally, there was a French graduate student who took Einstein's suggestion that light was basically also particles and decided that if light is a particle and it's also a wave, by that time light had been established as a wave. Therefore, what is wrong with assuming that electrons can also be waves? Okay, and that was the beginning of the concept of the wave-particle duality. Okay, and now comes the hard part. How do you reconcile these seemingly irreconcilable properties of matter? Okay, where objects that previously were massive now suddenly behave like waves, and objects that were previously waves now behave like particles. So a number of people tried to find a structure, a mathematical structure for understanding this. And Schrödinger, Heisenberg, Born, and Dirac were some of the key players in this field. Schrödinger was the first to succeed in establishing essentially rule or a mathematical structure that would predict the behavior of these particles, quote unquote, wave material matter also. And he was primarily inspired by Maxwell's electromagnetic equation, which most electrical engineers, actually all electrical engineers are aware of. And those equations, as most electrical engineers know, are really a statement for conservation of matter. They're conservation of charge in this case, and conservation of energy. So using that inspiration, Schrödinger said, well, why can't we treat this behavior as if it was a wave? So if we use a wave to describe it, we might be able to arrive somewhere. And he basically developed wave mechanics out of that inspiration. There were a lot, of course, of arguments against that, because what does the wave really then mean? What does the wave function itself mean? And he came up with this equation. And again, it was ad hoc. It's not easy to derive. And it worked, however. And these are the various, so the interpretation that he and Bohr attached to this, there was a group of scientists who basically assembled around Bohr in Denmark. They decided that maybe this wave should be the probability amplitude of finding an electron at a given place at a given time, okay? If you interpret it that way, then it matches Heisenberg's uncertainty principle, where it says that the electron doesn't really exist anywhere. It's a probabilistic fact. You can only talk about the probability of finding it at a certain location. You can't talk about its exactness, okay? And so using that argument, the law seemed to work, okay? And suddenly the mathematical structure was beginning to fall into place. And in order to account for all of the variables, people decided that maybe some of the mathematical operations are going to represent the observables, meaning the things that you can actually measure in the laboratory, okay? So the observers all of a sudden became mathematical operators, okay? And if you go that route, suddenly the structure seems to make a lot of sense, okay? And there were, of course, two sets of equations when you had the time-independent equation, and then you had the time-dependent equations to describe the dynamics when the particles are in motion. Okay, so the test of this equation then was to try to understand the hydrogen atom, one of the simplest atoms that you can imagine, okay? So because the hydrogen atom is in 3 dimensions, essentially that equation has to be set in 3 dimensions, in this case in spherical coordinates. Okay, you have a radius, and then you have the azimuthal and polar angles to describe what's going on there. And I have only written down the radio equation, and most electrical engineers know if you solve a differential equation, okay, the solutions you get are essentially quantized. In other words, they're specific. They depend on your boundary conditions, or if it's a time derivative, then it depends on your initial conditions, okay? And that equation then seems to argue for creation of quantization. In other words, you can't just have anything you want, and in this case, energy. You can't have any energy you want. The energies are going to be very specific. And that specificity is going to be defined by these things that became called the quantum numbers. And essentially, they describe the orbits that Bohr was talking about. And when you solve that equation in its entirety, given the parameters that were known at the time, the numerical parameters that were known at the time, you come up with an answer that actually matches experiment, okay? And then finally, of course, Einstein was watching this from the background, and one of the things he kept pointing out was that there was a problem with quantum mechanics. One of the problems was that it had to obey his law of special relativity, because at that time, he had already developed special relativity, which essentially says nothing can travel faster than the speed of light. And so to harmonize quantum theory with Einstein's relativity, Dirac came up with a different wave equation, which is a very, very elegant equation. It's also very complicated to understand initially. And that equation, purely from theoretical reasoning, he was able to predict particles that did not exist at the time. Much, much later, I think a couple of decades later, these particles were eventually discovered experimentally, and they matched exactly what he had said in his equations. And this equation is sometimes considered one of the most beautiful equations in science. So Dirac also, by the way, then was able to merge this quantum phenomena or this quantum theory with electromagnetic theory, because remember, Maxwell's equations describe light as a wave classically. In other words, rooted in Newton's way of thinking. Well, Dirac was able to begin the process of transforming electromagnetic theory also into quantized quantum theory. And there is a beautiful description of how he does that in his book, which essentially has remained one of the classic books in quantum theory. So the confirmation of all of this was measurement. And when the hydrogen atom was essentially placed in a vacuum light kind of a structure, and then you bombard it, you're able to measure the emission spectra. And this emission spectra match exactly the numbers predicted by the quantum theory and also by Schrödinger's equation. And so that was then the validation and confirmation that this theory had to be right. As bizarre as it was, there was something right about it because it was able to predict essentially reality. And then here comes the weirdness, okay? Thanks to Einstein, who raised a lot of issues with it, people were able to constantly go back to try to explain what was going on and to fix what was not right. And then, of course, he passed away before it was proven that some of the things he had worried about were not some things to worry about, that we don't really understand them. One of them was, of course, this idea of a quantum particle being able to move at different places at the same time. That was one of the things that he didn't really like about quantum mechanics. And then the other one was the fact that if you have two quantum particles that you prepare in a certain way, and then you take one of them to a different part of the world, the moment you measure the one that you have now here, let's say in Kerala, and then I'm in Pittsburgh, you gave me another, you have two quantum particles prepared in Kerala, one of them you sent to me in Pittsburgh. If you measure the one in Pittsburgh and you get the results, you know exactly what the results of the one in Pittsburgh are without even having measured it, okay? That was what Einstein called spooky action at a distance. And it now turns out that that is what is going to enable us to be able to do quantum computing, okay? It's a very controversial concept. It took a long time to actually verify experiments. Most of the experiments were actually verified in the 80s and 1990s, okay? And it's a very difficult concept to actually grapple with in terms of belief in it. It's almost like a religion. So the wave function today, of course, is interpreted as a probability amplitude. Its square represents the probability of finding an electron at a given time and a location, okay? So the concepts that are essential today for the second quantum revolution are superposition, okay? Superposition basically says that if you have a quantum particle and there is a multiplicity of states that it could be in, that quantum particle has the ability to occupy all of them at once, as long as you're not measuring it, okay? The moment you perform a measurement, then it has to make a definite decision on which state it's going to be in, and that's when you see that state, okay? Again, that's another unusual property. The second property is entanglement, which I just discussed briefly earlier. The way to think about entanglement, which makes a little bit more sense for most electrical engineers, is to think about correlations in probability. You're looking for mutual information between objects that are related. And we call that in typical electrical engineering language, we call that mutual information, okay? Information theory. If you think about it in those terms, then it makes sense mathematically. And then you have to try to ignore the physical reality that it's actually real, that two particles separated at distance can actually interact. And by the way, it's instantaneous. And then when you think about special relativity, which says nothing can travel at the speed of light, okay? So that's where Einstein's problem was that he did not really like this whole thing. He thought there were hidden variables somewhere that we were not understanding at the time. And he wrote this paper, which is now a very famous paper, the EPR paper, Einstein, Podolsky, and Rosen, where he actually makes the arguments against that whole concept. And people studied that paper for many, many years. And there was a scientist called Bell who eventually proved that there were no hidden variables, okay, mathematically. And then there was another scientist in France, Aspect, who later on proved that there actually was entanglement. It happens. And now it's fairly routine for electrical engineers to prove this concept using optics, that there's actually entanglement. You generate photons, single photons in a nonlinear crystal, and you can actually see the entanglement. It wasn't so simple then. Okay, so let me now give you an example of what some of these things have enabled. Because of quantum theory and the idea that solids and materials are made of atoms, we can now understand how these materials can be perfected. And what I show you is a portion of the periodic table, the section that most of the technologies that we enjoy today are based on, the electronic technologies. Silicon is the material of choice for most semiconductors. And then the materials to the left and right of it, the ones in yellow and blue, can be used as constituents that allow you to change the properties. For electrical engineering, this basically means you want to change the resistivity of the material, and that's how you change it by incorporating dopants. So using quantum theory, you can actually try to understand what a perfect silicon crystal would be like if you were to line it up and then using the uncertainty principle, allow it to bond and eventually form a solid, okay? And then using Schrödinger's wave equation, which is very complicated, it's a very difficult problem to solve because you're now solving it for many, many atoms. Most of the time, you don't need to solve it for many atoms. You can just solve it for a few atoms, and you can get the essential properties of the material, okay? And one of the results of that solution to this equation is that you can get semiconductors that basically say that depending on the particular material or beginning atom, okay, there is something called a band gap, okay? And band gap is essential for the operation of the transistors that we enjoy today. And then the band gap separates energies where electrons are and where they are free to move, if you can get them, give them the energy that they need. There are several ways of looking at this property. One of them is in real space, which is on the left-hand side. The other is in reciprocal space, or in electrical engineering language, that would be the Fourier space, okay? If you look at it in Fourier space, then what you get is a slightly different diagram, which also gives you a different side of the story, and nonetheless an important part of the story. The two sides of the story that you get from it is that semiconductors come in two varieties. One of them is called the direct gap semiconductor, where the minimum and the maximum of the so-called valence and conduction bands are directly overhead. That's the reason we call it direct. And then there's another set of semiconductors where the minimum and the maxima are offset. This is called indirect. And the consequences are tremendous, okay? Silicon is an indirect semiconductor. As a result, silicon does not generate light. In other words, you could never make LEDs or lasers out of silicon. That understanding can only be possible through quantum mechanics, okay? And so we have not tried to make light out of silicon, okay? On the other hand, we make light out of other semiconductors. The LEDs that you enjoy as lighting your houses or for your cars, they're made of a different kind of semiconductor. And that understanding, again, is possible because of quantum mechanics. So now that we know this, that was really what followed perfection of the semiconductors. In other words, creating the conditions so that they can be synthesized in the purest form so that you can actually now make devices out of them. And the consequence of that, of course, is the semiconductor and information revolution that we currently enjoy. And then one of the results was that if you decrease the size of a particular device, now the electron doesn't have very far to go, so it can travel faster. And that's how we've been increasing the speed of our devices. In other words, we increased the clock frequencies. Okay, and at one point, Intel had this cute commercial where they would say Intel Inside, and then they would mention the frequency at which their processors were operating. What that amounted to was they were just telling you that the devices were smaller, but that didn't sound very exciting. Telling you that they were very speedier sounded more exciting. So we are now leaving the realm where we took what nature gave us and we perfected it, or we created the conditions that allowed them to be made in a perfect form. And the next stage, which is the intermediate stage between the first revolution and the second revolution, is when we actually try to create materials that are deliberately smaller at the interface between atomic behavior and bulk material behavior. So if you took a semiconductor, large semiconductor, which is a centimeter, that's about the size of some chip in terms of the side, and you begin to reduce the size of that material, okay, all of a sudden you will begin to see different behaviors of that material. The first behavior that you would notice is that if the size of that device is on the order of the wavelength of light, the particular color of light that you pick, suddenly you have the ability to confine the light inside that material, okay? That's one behavior that you begin to observe. All of a sudden, you can now have optical waveguides, okay? If you continue to reduce the size of that semiconductor or material, you will reach a certain length, and that length, if it's identical or almost the size of a de Broglie wavelength, okay, quantum behavior cuts in. So the material can no longer be described by Newtonian or classical laws of physics. Okay, now you have to resort to quantum physics. And that's the realm of the revolution that started almost 20 years ago. When I was a graduate student, when I started working in this area, we were beginning to play with this regime where we would make quantum wells at the time. And then when I got my first job, I decided that why can't we make quantum dots instead? And then we started making quantum dots at the time because they mimic the artificial, they would be essentially artificial atoms. So how do you make that decision? Well, the way you make that decision is you take de Broglie's relationship and given the size of the electron, because the electron is essentially the particle that you're trying to confine or control, okay? You know its mass, you know the temperature at which these things need to be operating. And then there's this other variable, which is called Boltzmann's constant K. It comes out of a relationship I don't have time to go into. You can figure out what the dimensions are. And a particular size of semiconductor, you can actually determine exactly when the quantum regime cuts in, okay? And you can calculate that number exactly. And for a particular semiconductor, which we have worked with tremendously in my lab, which is indium gallium arsenide and gallium arsenide, the typical nanostructure sizes cut in at about 3 to 5 and or between 12 and 30 nanometers. Okay, in that range, we know for sure we will not be able to describe the behavior of electrons in that material using classical physics. Okay. And then we can actually go to the lab, and this is one of the most exciting things for especially for my undergraduate students, when you first convince them that they're going to see something that they cannot calculate using classical physics, and then they go to the lab and actually measure it, it's very exciting for them to be able to see that usually. Some of the properties that change, and I'm going to try to go through this without the details, is that in a bulk material, when I say bulk material, that's just conventional large material, a semiconductor. There is this thing called the density of electronic states. If you want to think about it as the positions that the electrons occupy. In a bulk material, that density of states depends on the energy quadratically, okay? The energy that the electron has. If you then form a quantum well is a two-dimensional structure where, think of it as a sandwich, okay? In a sandwich, you have two pieces of bread, and then in the middle is the meat, okay, or the cheese, okay? The size of the cheese would be your quantum well, and electrons can be confined in that sandwich between the two pieces of bread. And the energies that these electrons occupy, or the density of the states, is related inversely to the length or the size of that thickness of the sandwich. And then you can also create a quantum wire. And quantum wire is a little bit odd. It depends on a number of parameters. It depends on the area of the wire, because the wire has physical dimensions, okay? And also on the energy, okay? And then finally, when you get to a dot, the dot then behaves mathematically as a delta function, okay? So where you basically have, we talk of it as 0 dimensions, okay? Because the entity, in this case, the electron, is completely confined. It cannot move into any direction it prefers. And then all the properties of the atom, it now behaves like an atom. It essentially is an artificial atom, okay? So that's the realm of technology that's going to enable the, one of the technologies that's going to enable the quantum revolution, because suddenly we're able to make artificial atoms that behave the way real atoms do. Okay, so how do you make them? One way to try to make them, and it doesn't work, but let me describe it to you anyway, is to take, it's easy to make the sandwich where you have two pieces of bread and the cheese between them. That's fairly easy to make, okay? What's difficult to make is then to make it into a three-dimensional object that's really tiny, okay? Because then you need something called lithography, okay? For electrical engineers who are in the solid-state field, lithography is like doing photography, except you're using it for cutting and slicing pieces of material into a tiny piece. The problem with doing that is you introduce a lot of defects. All this cutting and sawing you're doing is very, very imperfect. It's almost like maram on the road, because at the atomic level, you're creating a lot of defects, okay? That's the reason why it doesn't work very well. And nobody, at least when we tried it initially, when people tried it in the early 1980s and late 1980s, this did not work because the imperfections that were built into the structure. The second method of making is chemistry, synthetic chemistry. For electrical engineers, they prefer not to do that because most electrical engineers don't know a lot of chemistry, or they don't like chemistry. They prefer physics, okay? And that's the way that we make them in my laboratory. We basically take a vacuum structure, and then we boil the atoms so that the atoms come out in molecular fluxes, and then we control the velocity of those fluxes. And we also control where they land. And by using computer programs, we can actually then have shutters. These are mechanical shutters or pneumatic shutters to control how long these fluxes are allowed on the surface. And that essentially controls the number of atoms that are incident on that surface, okay? We call that process molecular beam epitaxy. And there are various ways that you can control that. And here is an indication of how it actually works. I'm going to focus on the last one, the third one, which is that first you allow yourself to synthesize a very thin layer, and then you deliberately make sure that the layer on top is mismatched from the one at the bottom. And what I mean by mismatch is that the atomic registry, because remember, materials are atomically periodic, okay? So you basically make sure that the material at the bottom has a different atomic register from the one at the top. So it's like putting a sheet of rubber on top of a material. The rubber will shrink. It has the ability to shrink, and it also has the ability to expand, okay? So when you try to put more of these atoms on the surface, they then rebel. And then because of natural forces, they then prefer to conform into natural quantum dots because that's the minimum energy. Thermodynamics then drives the whole process at that point. You're no longer in control. Thermodynamics takes over, and thermodynamics basically requires that minimum energy be expended. And the way you expend minimum energy is to create these balls. And these balls are basically perfect quantum dots. And because nature made them, they don't have the imperfections that you have when you do it lithographically. And that's how we make them. So here's an optical micrograph of some of these dots that we make in my laboratory. Now, you can already see some of the tasks that are very difficult to make, okay? And that's also the reason why when people tell you that it's going to take a long time to make quantum computers, this is one of several problems that comes into play. Notice how we do not have registry. When I say registry, is that we do not have order. Yes, I have succeeded in growing dots, but they are not ordered. In other words, I don't see them in a line or in a row or in a kind of a structure, okay? Each of those dots represents tens of thousands of atoms now. And that cluster, I can now use quantum mechanical equations to describe how it behaves, okay? And I can measure exactly what the sizes of those dots are. And this is using metrology, which I mentioned earlier. Using the metrology technologies that we have, I can measure down to several atomic layers. And here's an example of it, okay, where I can now measure the size of a dot. The lateral dimension is about 14 nanometers, and the height is about 3 nanometers. That's several atoms in height, essentially, or as we like to say, several atomic monolayers. And here's our attempt at trying to learn how to order these crystals. This now involves an interplay of computer simulations, modeling, and physics, and of course, electrical engineering. And in order to be able to force these structures to self-organize, what we've done here is we've done a mathematical modeling of what the forces should be to balance out, and then to basically force one of those dots to land on top of the other, because that's the minimum energy position, okay? Obviously, when you go to the lab, you haven't succeeded in all cases, okay? The calculation tells you it will happen, but then you have to go to the lab and make it happen, and it didn't in this particular instance, okay? Because the conditions were not quite right. So now you kind of hopefully get a sense of how difficult it is to make these structures for the second quantum revolution. It's not trivial, okay? And here's an attempt at trying to make a superlattice array where we vertically stack them, and we basically miserably failed in the first attempt. And then in the second attempt, we are successful. So the computer model basically told us it will happen. We went to the lab, created the right conditions, and it did happen. Now we have stacked these atoms. Each one of them, in this case, I think there were about 50 of them, 50 dots are vertically stacked. And now you can see the beauty of it is that it's very easy now to have a mathematical model to model the behavior of this and to be able to predict the properties for the one on the right-hand side. The one on the left is completely random. It's very difficult to put a mathematical structure to it, okay? It took us several years to learn how to do this, okay? And this is one of the benefits of having graduate students, because they're very good at taking something and doing it over and over again until they succeed at doing it. So how does this work? Okay, what is the physics behind it? Essentially, what we've now created is that instead of having a continuous energy, if you think of this as the conduction band, and here is the valence band, and here's the conduction band. All of a sudden, the quantum dot now has an energy structure that looks like this. I have a lower level and a higher excited level. With this kind of a structure, now I can begin to build very sophisticated electronic and photonic devices, okay, which hopefully will enable the quantum revolution. In other words, now I have exquisite control of what the electron can or cannot do, okay? In this example, if I now introduce the dopants I mentioned earlier, now I can choose not to populate this energy structure at the bottom and only populate the one above. And that's called Fermi level engineering. And I can basically do that. And all of a sudden, now, when I shine light onto this structure, the electron can be excited, and then I can generate a current. And that current, I can create all sorts of interesting electrical devices or photonic devices out of it. One of the things that has to be obeyed is several of the quantum rules now come into play. Things like, what are the rules for absorption and emission of light, okay? And without going through the details of it, I can make those rules to be obeyed in this structure, which I cannot do in a conventional material, okay? And here's what I mean by that. For those of you who are electrical engineers in the audience, you know that light is a transverse phenomenon, meaning that light travels in a direction where the electric field is oscillating orthogonal to the direction of travel, okay? That's what we mean by transverse. Now, that light field has to interact with the electron, okay? Because of the nature of a quantum well, that interaction is basically forbidden, because those vectors, if again, for electrical engineers among you, if you have two orthogonal vectors, the dot product of those vectors is 0, okay? So you see the electron vector, which is this thing over here in the Gaia-Marsden quantum well, is going up and down. The light vector is going orthogonal to it, so there will be no interaction between the light and the quantum electron in the quantum well, okay? On the other hand, in the quantum dot, because of the way the quantum dot forces the electron to behave, there is always a component of that vector that interacts with the component of the light, and therefore you have absorption, which is good for devices. The other thing that also happens in these structures is that you control the lifetime. We call it the excited lifetime. In other words, electrons always prefer to be in the lowest energy state, just like you prefer to always sit down instead of standing up. Electrons do the same thing. So in a quantum well, electrons don't live very long in the excited state, okay? It's only about 2 to 5 picoseconds, okay? On the other hand, in a quantum dot, they can live much longer, which is good, which allows you to do a lot of manipulations that are necessary if you're trying to perform a certain operation with this device once you've made it into a device, okay? And one of the devices that we've made over the years and succeeded in making is a night vision camera, okay? The night vision camera only sees at night. And the reason it only sees at night is because it uses infrared photons, okay? In other words, your body emits heat at night. All bodies emit heat at night. And if I'm able to detect that heat that's emitted, I can see you if I have one of these cameras. So we set that as one of our goals, and we did succeed in making it, but it took us 6 years to make it, to succeed at doing that. And the way we did it basically was by stacking up the quantum dots, as I showed earlier. And then this is one of the, this is what the energy structure looks like. And then here's the circuit outside of it. And then the electrons are basically excited into the continuum states. And then at the continuum state, we can collect them as current. And when we can collect them as current, we can now do all the electrical engineering and computer science processing. In other words, we can now do we have the data, now we can do the image processing, okay? We can now write at the macro level, we can write computer programs to manipulate the data so we can get the image out of it. And this is one of the characteristics of the device. Here is a linear array of those devices. And one of the goals of this project was to make this thing work at room temperature, because again, this is one of the problems with quantum events. They don't like to be at warm temperatures. This is one of the reasons why the current generation of quantum computers that IBM and some of the other companies have tried to make only operate at 0 degrees Kelvin, okay? Now, we tried to make this sensor to work at room temperature. We failed. However, we did get up to 222 degrees Kelvin, which is extremely warm, which means that you only now need a very small cooling system designed with the camera so you can make it operational. Now, this work was funded by the US Army because they're interested in seeing at night. And they specifically set the goal that we have to make this work at room temperature. So that's why it took 6 years to actually get to the camera. And here is the camera that we ended up making. This is one of my graduate students who basically wanted to take a picture of me in the dark because of my dark complexion. He wanted to make sure he could just, when he shows up at his thesis defense, all he had to show was that picture that I need to graduate. I succeeded in my experiment. So let's now look at what the world is investing in for the next quantum generation. People are investing in quantum clocks. These are important and they can be made with trapped ions and atoms. And they allow you to measure time with precision that you haven't seen before. Why is that important? Again, going back to my introduction, that goes to GPS clocks. If you can make GPS clocks, that means the resolution of your location, space location, you can bring it down to a few millimeters, okay? Quantum sensors, you're able to detect very, very weak electromagnetic fields and gravity fields, which means lots of explorations for oil, because if you can excavate for oil or gas, all you need to do is measure the gravity, the changes of the gravity fields, and quantum sensors can do that for you. If you want to measure brain activity, the electromagnetic fields are very weak, you can use quantum sensors. Quantum imaging, you can potentially be able to see around the corners using quantum sensors or quantum imagers. And the way that happens, and this has actually been demonstrated a few times now, is that you can measure the arrival time of single photons, okay, after they've been reflected off or diffracted off an object that's around the corner. And then finally, you can do quantum computing and quantum communications, okay? And the reason why people are so excited about quantum computing as opposed to the other applications is because of the fact that there are things that quantum computers can do that classical computers can't do. So if you recall my discussion on superposition and entanglement, what that means is that if you have a quantum bit, okay, that bit is in a superposition with all other possible states it could be in. So that means if you're able to make a quantum register, okay, instead of having your von Neumann architecture of the computer where you're shuttling information back from memory to the active register for processing, what then happens is that the quantum register is able to give you simultaneously in parallel all the possible conditions, okay, and process that information. So in other words, it's able to operate in parallel very naturally because of superposition and entanglement. The other thing that it will be able to do is it's also very, very good at factoring large numbers. This is essentially interferometry, okay, and that happens because of the wave nature of the quantum particles. And the most famous algorithm is Shor's algorithm. Okay, and this is the basis of cryptography and computer security. That's one of the reasons why people are so excited about it. It essentially means if you have a quantum computer, people with classical computers have no security at all because their codes can be broken at any time. The other excitement centers around Grover's algorithm, quantum algorithm, which basically is for searching large databases. If you look at a phone book in the days that people had phone books, if you wanted to find someone's number and you know their name, you just go down alphabetically and you find their name and you'll get the number, right? Now, suppose that you don't know the name, but you have a mass of numbers, okay? How do you find that right number? Well, it turns out using a quantum computer, you can exponentially go faster and find exactly what you're looking for. So that's one of the excitements, okay? The other reason also is because quantum computers are naturally obeying quantum rules. If you wanted to simulate a new material built from scratch, it would be possible to basically build it up from the constituent parts and be able to do it from scratch. And the simulation will be optimized, okay? Simply because you have a quantum computer. So here is a quantum bit, okay? And this is just to illustrate the idea of superposition I mentioned earlier. So in a normal computer, you have a 0 and a 1, and these are very distinct states, right? In a quantum computer, what you have is this sphere, it's called the block sphere, which illustrates essentially the idea that if you have a quantum bit, it's in a superposition, okay? And it could be any one of those positions on the surface of that sphere. So that kind of gives you, this is a single bit. Now imagine you have a register of all of them. So you have lots of spheres like this. Now you have a multiplicity, a huge number. We call this thing the Hilbert space, okay? So this Hilbert space is basically an infinite set of states possible. And that's really where the excitement is. Here are the challenges, however, to building this, okay? One of the requirements of this Hilbert space for computation is that these qubits or quantum bits have to be entangled, and they have to be well isolated from the environment, and they have to be well controlled. And as I've already illustrated in the discussion on quantum dots, it's extremely difficult to control these things, right? And the other need for isolation, well, because you need to be, this has to do with entanglement. The moment you actually allow it to interact with the environment, you destroy the quantum properties, okay? So that's the reason why a lot of the quantum experiments are typically done in a vacuum at low temperature. And those are technologies that are actually very difficult to achieve in their own right, okay? Now, the need for these conditions impose challenges that are very difficult to meet all at once: the thermal, vibrational, and an electromagnetic environmental isolation. They're very, very difficult. There are a number of current technologies that are being pursued for qubits, because you need to make physical qubits to be able to make your sensors and computers, quantum properties. The simplest one is superconducting Josephson junctions. This was invented at IBM a long time ago, and it's the one IBM is pursuing. Unfortunately, that also requires cooling to 0 degrees Kelvin. So you need refrigerators for that. And then there's trapped ions, which you trap by using lasers, okay? And then there's the quantum dots that I talked about, okay? And then there's photons. The photons and the quantum go together, because in order to generate single photons, one of the ways you can do it is basically by using quantum dots. And then the other, of course, is by using nonlinear processes. So in order to be successful, the ultimate technology chosen for the qubits has to be manufacturable at scale. And that basically means you have to be able to manufacture them repeatably and reproducibly thousands and thousands, if not billions and billions of times. This is currently a very, very challenging task to accomplish. And that's one of the reasons why when people say a quantum computer is not going to be around for maybe 5 to 10 or 20 years. All right, so what does the global landscape look like? This is how countries are investing. As of 2020, $22 billion have been invested in quantum technology. Almost all countries are investing, except for the sub-Saharan Africa and Brazil, and then the small islands in the Pacific and Mexico that are not investing in quantum technology. So clearly the stakes are very, very high, and everybody seems to recognize why the stakes are very high. So let's just see why the stakes are so high. What would be the impact of quantum technology on science, okay? On science alone, scientists will be able to do simulations that they cannot do today, okay? And I'm talking about simulations for creating new materials. Since these materials are created out of quantum particles, you can now actually simulate them at the atomic level exactly using a quantum computer, because it can do it, okay? Genetics. Most diseases originate from genetics, from the genes, okay? Are inherited from the genes. If you can manipulate the genetic code and understand it using supercomputers, you can pinpoint where the errors are that are causing this disease, and you can fix them. There is this thing called, it just skips my mind, but it'll come back later. There is a method for editing genes nowadays. That was awarded the Nobel Prize actually last year. Maybe if you can have a supercomputer, you'll be able to define what kind of chemistry you need to be able to fix some of these diseases. And that basically means churning through a lot of combinations of drugs to be able to pinpoint which one would affect a certain defect in the genetic code, okay? And only a quantum computer could do that because of the many choices that you have to go through. And then eventually, if people are interested in mapping the human mind, to try to understand the human mind, there's just not enough computer power in today's classical computers. You could do it using quantum computers, okay? Economy. Countries that master this technology will create new industries, new products, new services, and employment opportunities for their citizens, okay? If you have the manufacturing infrastructure, you're likely to become a dominant global economy while lifting the standards of living for your citizens at the same time. Financial markets are going to rely on the security of quantum computer transactions. And manufacturing is going to rely on quantum computing because a lot of the simulations, in other words, before you make any product, you're going to try to optimize them by simulation and modeling so that it's cheaper to make. National security. Most of the technologies that are involved in quantum technologies have national security implications. Being able to navigate around the world without conventional GPS, for example, by just knowing the magnetic fields of the Earth, okay? Being able to store your information securely, being able to create defensive weapons that operate on their own capabilities because they have quantum computer capabilities, okay? One of the things that's going to be very difficult is control of national identity, destiny. Okay. Trickle-down effects will obviously help developing nations, but it will make their continual struggle to catch up harder and widen the gap of inequality. Industrial dominance. A lot of these industries are going to be affected by quantum technologies. Aerospace is one. Defense, healthcare, finance, and information technology. They're all going to be affected by quantum technologies. That's the reason why a lot of countries are investing in them. Okay. So the countries that are able to invest in research, innovation, and education, more importantly, of the science and engineering fields that are relevant to this technology are the ones that are going to benefit most. Okay. Unlike previous developments in science, the barrier to entry is extremely high for the quantum enterprise. And what I mean by that is that it requires a lot of financial investments, large financial investments, and a lot of sophisticated equipment and highly trained personnel. So quantum technology is basically a whole promise for a lot of things that we don't currently understand, but we'll be able to understand. At the same time, will also give us new technologies that will hopefully improve lives for all. Okay. Because of the many different fields involved, it will require collaboration. In other words, the days of the single scientist working alone or working in their unique field are gone. If you want to work in this field, you have to be able to collaborate with pure mathematicians, computer scientists, physicists, electrical engineers, mechanical engineers, to be able to accomplish this goal. This enterprise is already beginning to restructure how educational programs are run. Okay. I know it at my own university, it's beginning to do that. And also it's beginning to create industries, new industries and new jobs for the future. I want to acknowledge support for my work from the US Army, the US DARPA, and the National Science Foundation. And then, of course, my graduate students who have been involved in this work. These are some of the students who did some of the work that I talked about in the quantum dot area. Most of them are now either running a company or working for a company somewhere. This is the equipment that essentially that we've been using. And this is what I mean by it requires a lot of infrastructure that's expensive. in my group, we have these two systems, these molecular beam epitaxy systems. Each one of them is about $1.5 million each. And each one of them requires liquid nitrogen. That's what you see going to the ceiling. That's the conduit for liquid nitrogen, which has to run like water every day. When the students turn it on in the morning at 9, they don't turn it off until 10 o'clock at night. And unfortunately, liquid nitrogen costs more than water, so it's not cheap. On a typical day, when they're running both systems, we spend about $700 a day, essentially, to be able to run the experiments. Thank you for your attention.
Hello, sir.
Well,
Hello, thank you so much, sir. That was a wonderful presentation. I hope that most of the audience have gained a lot of information from that presentation of yours. And we see in the chat that there are some questions awaiting you. Can
sure.
we move on to the question answering session?
Yes, please.
The question is from Sajida. She's saying that China is investing 10 times that of any other country or region. So what is the implication of that?
Well, it basically means they're going to reach the end goal faster than everybody else. At least that's what you can infer from it. You have to remember, China has a very large population of young people at universities. So a large investment basically means they're going to be able to train a lot of people very highly in this field. And if all things work out, they're going to be able to basically begin to deploy these technologies and be able to manufacture them at a much larger scale than anybody else can. That's really what it means. Now, the political implications of it, I'm not a politician, I don't know, but I'm sure there's a lot of political implications for that.
Okay, sir, thank you. So the next question is from Harindral, sir. Will you please put light on the quantum of investment India places compared to other countries?
I'm not very aware of, there is some funding, I know that, because one of my students, former students actually is at Indore. He works at the Indian Atomic Agency, which has, recently they purchased an MOCVD system. And last year he was talking to me about helping him make a case for an MBE system. So there is some investment in India. And I also know that the IIS in Bhopal is investing in this field. And I have had students from Kharagpur, IIT Kharagpur in my group. And I know that there's several professors in that university. Now, the Indian Atomic Agency and Indian Space Agency has an MBE system. I know that. I think there's at least 4 MBE systems in India that I'm aware of. And I've had students come from those labs. So there is some investment. I don't know exactly what the dollar value is. The number that I showed from that website, I cannot verify that because I'm not aware how they got that number. The other numbers are sort of have other alternative means of checking. I know for sure that the other numbers are quite correct.
Okay, sir, thank you. The next question is from Narayan Kuti, sir. The educational requirements will undergo drastic changes with the advent of quantum technology. Can you elaborate on this?
Well, it basically means, let me give you an example. When I was a student, as an electrical and computer engineering student, one of the requirements at my university at the time was that I had to take quantum theory and statistical mechanics, okay? And then when I was a senior student, suddenly that rule was abolished. It was no longer necessary for an electrical and computer engineering student to take any of those courses. And the feeling at the time, this is the late 80s, the feeling at the time was that the semiconductors that require you to understand quantum theory was silicon. And silicon at that time in the 80s was very well understood. So why are we making our students take courses they will never use? So that was the logic. And then I was hired at Carnegie Mellon, and suddenly they realized that, you know what, this requirement may not be a very good thing. Yes, we're not going to make our students take quantum theory, but if a particular professor wants their students to have that background, he's going to have to work with the students to convince them to take a physics course in quantum theory. And that's essentially what I've done at Carnegie Mellon, where if you want to work in my group, the first thing I ask you is how much quantum you have. If you don't have it, I say, well, okay, in addition to your electrical engineering and computer engineering load, here's a requirement I'm going to stack on top of that. And they usually do that. At other universities, and I know MIT and Harvard and Stanford are now doing it, the requirement is now coming back to the electrical and computer engineering departments, where they're not making it a rule yet, but they are basically suggesting that any students who really want to work in this field should take courses across the field, mostly number theory in mathematics, of course, and regular differential equations, and then group theory. These are our mathematics courses. And then probability, of course. And then in the physics department, you need to take quantum mechanics, at least 2 levels of quantum mechanics, and statistical mechanics. And then your regular complement of the slew of courses that an electrical engineer would take, things like, you know, algorithms, computer architecture, because you still need to understand that, robotics, and all the other courses that a typical electrical and computer engineering person would take.
Thank you, sir. So the next question is from Malla Bhaskara Rao. The question is, what is the time frame for translation required from lab to the product development?
That depends on the product. There are already some products in the market, quantum products in the market. The simplest one that went into production or into the market last year was you can now buy atomic clocks. These are extremely precise clocks. I don't know what you would use one for, but they are now available from a company in Maryland in the United States. And I think there's a French company that will also sell them. But the time frame for the other products, such as the sensors, is expected to be about 5 years. And for the quantum computer, no one really knows. I mean, the 3 large companies in the US that are working in these fields, Google, Microsoft, IBM, and Amazon. Of those companies, Google and IBM are the ones that have a prototype in their laboratories. IBM has offered their computer on, you can log onto their web. At least last year, it was available to anyone. There's long lines, you have to wait. You can log in onto their computer. You have to sign up for it, and they will allow you to run programs on their quantum computer. But it only had, at the time that they offered it, only had 20 qubits. Now, 20 qubits may sound like a very small number, but remember that it's 2 to the 27. So it's exponential.
Okay, sir. Can you explain more about the possible forces playing in spooky action at a distance? The question is from Rahul Ratnakumar. Okay, so should I repeat the question for you?
Yes, please.
Can you explain more about the possible forces playing in spooky action at a distance?
There are really no forces, okay? This is a very difficult question, and I am not an Einstein. Even he struggled with it. That's why he came up with the word spooky. The way to think about this, at least the way I like to think about it, is a probability. It's a mathematical thing. And in probability and communication theory, in electrical engineering, there is this thing we call mutual information. In other words, if I'm going to transmit a certain piece of information, and there's interference from, let's say, the another source of information or another channel, let me use electrical engineering language, from another channel, what I'd like to do is to eliminate that interference so that I reduce the mutual information to 0, okay? Or at least minimize it. So now what it really means, this entanglement, which is this spooky action of that action, is the fact that if I prepare two particles, which is equivalent to two channels in communication, and these channels are entangled, if I now separate them, they carry along that entanglement. In other words, they carry along pieces of information from the other channel, and it will still have that piece of information. If I measure it on the other removed channel at a distance, I know exactly what other information that other channel, which is now away from me, has. That's the only way I know how to understand it myself that makes sense to me. Because if I think about it from a physics point of view and what the forces are, then I run into the problem of we cannot have things traveling at the speed of light. And I would have to explain that. In other words, a force vector would have to instantaneously travel at the speed of light or faster, which I know is impossible according to the special theory of relativity. Then how do I explain that? So it's a very difficult concept, and no wonder it took so many years. Actually, it took a good part of 3/4 of a century for people to come to terms with it.
Okay, so the next question is from Dr. Ann Panika. Self-organizing by epitaxy. Would you explain with an example?
Okay, how the epitaxy works? Okay, the way it works in our case is that we have essentially 6 sources. And what I mean by sources is that we have pockets of high purity materials in vacuum, and they are simultaneously heated and cooled. And what happens is that we heat them, and by heating them, we create molecules out of them. They come out as gases. There's molecular flux. They travel to our substrate. And at the substrate, this is another piece of semiconductor. Because of the atomic registry, in other words, there's a periodic structure on the surface of the substrate. And my molecules that are traveling in vacuum towards that substrate will land and begin to bond. They will form atomic bonds. And ideally, under thermodynamic equilibrium, what they prefer to be at is the minimum energy of bonding. But if I introduce an atom that has a larger, let's say, radius, it wants to form a periodic structure on the crystal that has a much larger periodicity. So that creates strain. So there is now a mismatch in the atomic registry. Now, that atomic registry can only be withstood. In other words, because these things are elastic, remember? So it will only be withstood up to a certain thickness. If I try to go beyond that thickness, and the way I go beyond that thickness is by allowing the time of arrival of more atoms, okay? Then this atom basically snaps apart. And then thermodynamics takes over. And when thermodynamics takes over, it rearranges the crystal. And at that time, my computer program has shut off the arrival of the atoms, okay, on the surface. And the thermodynamics takes over and rearranges these particles to have the minimum energy. And that minimum energy surface area, it's like a bubble. If you ever blew a bubble as a child, when you blow the bubble, it forms a sphere, right? That's a minimum energy condition, essentially. You take a soap bubble and you blow it, and the first thing you see is a spherical shape. That spherical shape is a result of thermodynamics because it's trying to constrain the structure into a minimum energy. That's exactly the same thing that happens on the surface of the crystal. So that's how we form the self-organizing quantum dots. I hope that makes sense.
Yes, sir, definitely. Next question is from Sahir Bashir. Actually, he has a doubt regarding slide number 9. He says that you wrote H across Planck's constant. Isn't H across Planck's constant divided by 2 pi? Can you please clarify his doubt?
Yes, let me explain that. Let me see if I can get slide 9.
Is the audio working or?
Yes, ma'am. The audio is working. I think
Okay,
Sir has gone to put up the presentation for us to clarify the doubt on slide number 9. Elias, sir, are you there?
Let me check. Yeah. Okay.
Okay, ma'am.
I think he lost the connection. He's rejoining.
Oh, thank you, ma'am.
Are you connected now? I think we don't. Harinderlal sir, I think he needs you to unmute him. Somebody's got music on. Harinderlal sir?
I can hear you. No, yeah.
Can you unmute Professor Towe? He says you have to unmute.
No, his
Sir, please assign him as the co-host.
mic is not on. His mic is
Sir,
not
just
on,
below
not
the-
connected. His mic is not connected.
Let me check.
I think he may have to rejoin.
Okay, just a minute. Harinderlal sir, he says that the host is not allowing the participants to unmute.
No, his mic is not on.
Your mic is not on. It's not showing your mic that your mic
Yeah.
is on, sir, Professor.
Yeah, he may have to rejoin if it is not.
Prof, your mic is not on. No, it's not showing as on here.
I don't see the mic icon. He may have to rejoin, Sajita. disconnect and join.
Okay, he says that you have to unmute him, but we don't see his mic.
Yeah. No, the one solution is he has to disconnect and rejoin.
Yeah.
You will see.
Can you disconnect and rejoin again? Yeah. Okay. I think it still says it's connecting, right, to audio. Have you, Ethel, sir, have you seen the message?
Yes, now I think.
Yeah, he is on.
Okay.
Okay, so I was responding to the question on H bar on the Schrödinger equation. There are basically two ways of writing the Schrödinger equation: one with the H bar, or one with H without the division by 2 pi. And the way I have written it there is essentially when you consider it as an operator. In other words, when you consider the kinetic energy as an operator. And when you do that, essentially you're using the fact that the momentum is k, where k is the momentum in quantum mechanics, and it's given by 2 pi over lambda. So that's where the 2 pi comes from.
Okay, sir, thank you. So the next question is from Zahir Bashir. I have read that carbon or graphene-based electronics would be much faster than silicon electronics. Is this linked to quantum computing?
Yes and no. The reason why graphene has unusual properties. First of all, it's a single atomic material. That's one of the unusual properties that it has. But there is a problem with graphene. You cannot make it out of, you cannot make computers out of graphene, even though people at Stanford have tried using carbon nanotubes, which are a derivative of graphene. The reason is graphene does not have a band gap. In order to have a switching device, you need a band gap. That's the reason why silicon works so well for digital electronics and all the electronics we enjoy today, is because of the band gap. The band gap allows the material to switch. You cannot have a zero band gap semiconductor to make a switching device out of. That's the reason.
Thank you, sir. That was the last question.
We will move to the next one because the time is up.
Yes, sir. We will move on to the vote of thanks. Okay, so let me welcome Elias Towe, sir, to propose the vote of thanks. Sir, please.
Okay, am I audible to everybody?
Yes, sir, you're audible.
Okay, good day and happy new year to all. Today we had the 39th talk of the Intersociety weekly webinar series. The regular Wednesday tech talks held in the Institutional Engineer Hall before COVID lockdown took shape of a webinar from April 15, 2019. This program is jointly organized by IEEE Kerala section, IE India, Computer Society of India, Project Management Institute, Internet Society, IEEE EMBS, and Vakkom Foundation Trust. 38 talks were arranged in 2019 on a variety of topics of contemporary importance by very eminent speakers. A.G. Harinder Lal is the man behind this great show. No words can portray his dedication and commitment in making it a successful and popular program. I also thank leaders of all partner organizations for their magnificent spirit and support. Today's topic, the promise and implication of quantum science and technology, a revolution like no other, has far-reaching significance. We are very lucky to have Professor Elias Towe, professor in Carnegie Mellon University, who is an authority to talk to us on this subject. He took us back to our college days, reminding of classic physics and quantum physics, wave particle duality, Schrödinger principle, Pauli substitution principle, Einstein, Heisenberg, Dirac, de Broglie, and so on. We are currently in the midst of a second quantum revolution. The first quantum revolution gave us new rules that govern physical reality. The second quantum revolution will take these rules and use them to develop new technologies. The hallmark of the second quantum revolution is the realization that we humans are no longer passive observers of the quantum world that nature has given us. In the first quantum revolution, we used quantum mechanics to understand what already existed. We could explain the periodic table, but not design and build our own atoms. We could explain how metals and semiconductors behaved, but not do much to manipulate their behavior. The difference between science and technology is the ability to engineer your surroundings to your own ends and not just explain them. In the second quantum revolution, we are now actively employing quantum mechanics to alter the quantum face of our physical world. Thanks to Professor Towe for brilliantly exposing us to where the technology is taking us to. Thanks, Professor, for your valuable time and effort. We thoroughly enjoyed your session. Now it's time for a virtual memento to be presented to Professor Towe. Thank you, message.
Thank you so much, sir. Once again, we would like to extend our sincere gratitude to our honorable chief guest, Professor Towe, for taking precious time out of your busy schedule to be here and for sharing with us your valuable ideas and thoughts on this very important topic. It was a very informative session, sir. And if you check the chat box, you could see the chat box is filled with messages from all the participants saying how magnificent the presentation was. Thank you so much, sir.
Next,
Thank you very much.
Next, thanks to Dr. Sajida Bashir, the Vice Chair of Vakkom Foundation Trust and Advisor, Global Education World Bank Office, Washington, D.C., who arranged this talk and introduced the speaker brilliantly. I also thank Bhagyasri for moderating the session, Athena Nixon for welcoming the participants and honorable guests, technical support team for the excellent work they have done. And finally, we have very many senior people attending this program from various parts of the world. They are the real spirit of this program. We are motivated by their presence and interest in this program that makes us go from steps higher to higher steps. Thank you all for participating and supporting this event program. Thank you.
Thank you, Suhair, sir.